Okay, now we're moving on to the last lecture, lecture 19 on electronic countermeasures, also known by the acronym ECM. Let's take it to the end. Wait for the fat lady to sing at the end of this lecture. Okay, here's our last time. We're going to show you the block diagram of the radar. And what we have here out here is a target that the radar is interested in seeing. And we have another aircraft, or it could be a ground-based transmitting jamming signal. On the aircraft, you could also have chaff, which is false targets. We're going to describe in detail what chaff is, which can cover an area with false targets, or small ones, or a big area. We're going to talk about that whole process of how one denigrates the performance of a radar from other emitters, such as jammers or chaff. And we're going to look at those techniques. Okay? And generally, this is descriptive of how these systems work. Okay? Now let's move on. And notice it's another signal coming in, which could be backscatter from the chaff or emitted from a transmitter in a jamming aircraft that will go into the antenna, mixed with the echo, and we hope not drown out the echo from the target of interest. Now let's move on. It basically divides itself into just these categories: electronic countermeasures, and then countermeasures, how you counter the countermeasures, and then a summary. First, we have a cartoon. Here we have a couple of radars, ships, we've got ground clutter to deal with, and we've got hostile aircraft that we want to see. And we've got airborne early warning aircraft, and out here we can have an enemy that's hostile, and that have airborne jammers, and also may have chaff also to clutter up things in the radar processing. And what they can do is they can deny the radars on the ship's radar on the ground to see hostile aircraft that are coming in to attack your forces, like these ships. Hostile aircraft coming to attack the ships. You'd like these ships to make sure that this one looks like an Aegis destroyer. You'd like this destroyer to be able to see these hostile aircraft and not have their performance denigrated, so that they can't be seen, would get close, and possibly damage or sink the ships. So that's the environment we're working with. Now, what I'm going to be doing is broken up this whole issue of electronic warfare into a set of boxes, block diagram. And this was I've taken from a set of lectures that I've re-rendered the stuff from a briefing that Dave Barton, first people to write good books on radar after the Rad Lab series. 40 years ago, when I was just learning radar, Dave Barton had one of the best books out on radar systems, and one of the first, along with Merrill Skolnick. And anyway, he gave a lecture at Lincoln Laboratory, and an unclassified lecture, and he used this breakdown, and I'm using it also, and I just like to say thanks to Dave so we break down electronic warfare into three things: electronic support measures, which are means to identify the characteristics of emitters, like radars or communication systems. These systems are classified, so just not going to discuss them. And electronic countermeasures, they're going to be discussed. And electronic countermeasures, we break up into three areas: masking, so that denies you from seeing the target; deception, fools you, the target might be somewhere else rather than where the radar echo tells you it is; or destruction, you physically destroy the target. We'll talk about that. Physically destroy the radar. We'll talk about that. So these two areas will be discussed, and this one will be broken down. So there are going to be 4 areas we're going to discuss one at a time. So first, let's look at electronic countermeasures, ECM. masking, deception, and destruction. First will be masking. And in masking, there are two things that you can do. One is you can make the target so small, its radar cross-section so small, that you can't see it. We've all heard of the F-117 stealth fighter, the B-2 bomber stealth aircraft. People talk about in the news that unmanned aircraft like Predator, they have stealth capabilities. These, to the extent one can talk in an open literature, we talked about radar cross-sections to some degree in the targets lecture, but all of this stuff is really classified and we can't go into it. But the one area you can go into, and we're going to focus on quite a bit on, is chaff. And that's what we're going to start focusing on now. Well, what are the attributes of chaff? It's a large number of resonant dipoles. They're a half wavelength in length, and they're either metallic or metallic coated. They could be Teflon with metallic coating. And they have a high reflectivity per pound. Resonant dipoles do. And the optimum length is a half of a radar wavelength. And what you do is you'd have a case with them, and you'd drop them out and disperse them in the wind. And they move horizontally with the wind. And what are the uses? Well, first, masking. A large cloud can shield aircraft or missiles in and near the cloud. So, and it's diffuse clutter. It appears to in the radar, and it's very similar to rain. Only it has a much higher cross-section than rain does. And deception chaff can be a puff of chaff that emulates a missile or an aircraft and can cause false detections. If you've ever seen on the news when fighter aircraft are trying to avoid a heat-seeking missile, they drop out flares one after the other, and on one trajectory, say to the left of the rear of the aircraft, while the aircraft goes to the right, and these flares have a much higher infrared signature, and that you hope that the infrared tracking missile will follow the flares. In the same way, if a radar is looking at you, you can put up puffs of chaff, which will appear like a false aircraft track, and the missile that's trying to knock you down will follow the chaff rather than the aircraft. And these, as I said, this is repeating it, these packets of chaff seated in a row can cause a radar tracker to track the chaff rather than the aircraft being tracked. Okay, now how big are they? Well, these resonant dipoles, the maximum cross-section per dipole is 0.86 lambda squared. It's a pretty simple target cross-section calculation where the wavelength is in meters. And randomly oriented large number of dipoles, the cross-section is 0.18 lambda squared in meters squared. And that's the average cross-section per dipole. Now, if you take aluminum foil dipoles that are 1/1000th of an inch thick, you don't have to have them very big, and 1/100th of an inch wide and a half a wavelength long, then this is a really good rule of thumb that the cross-section of the whole chaff bundle, before you disperse it in the wind, and I'll show you how that's done, or one of the ways it's done, is equal to 3,000 times the weight in pounds of the chaff dipoles, the total weight, divided by the frequency in gigahertz, and the weight is in pounds, and that gives you the cross-section in meters squared. So at a 10 centimeter wavelength, S-band, 400 pounds of chaff, which you quite readily could put in the wing of a pod under a wing of an aircraft, will amount to 400,000 meters squared of cross-section. If you dropped, say, 100 meters squared of chaff, you could fill up 4,000 range azimuth cells with clutter that would be 36 dBSM, bigger than a target. So you can really cloud up a big area, as you'll see. Now, the properties of chaff, it has a bandwidth of 10 to 15% of the center frequency, and so that means that if you want chaff that's going to blanket one radar at one frequency, you can tune the length of the chaff to that. But if you've got radars of all different frequencies, you're going to have to cover a lot of different bands. And wideband chaff has been made that operates from 1 to 10 gigahertz, a lot more than this, just 10%, and it's 60 pounds, 60 meters squared per pound, and you use variable length dipoles in a single package. And the fall rate of chaff is about 1/2 to 3 meters per second, and it depends on whether, I said Teflon earlier, I meant nylon, excuse me. Nylon-coated chaff drops at about 0.6 meters per second, and then aluminum and copper. So it stays up a while, and we're going to show you a nice movie of that stuff. And this is what the frequency response of resonant chaff is. Notice this is a log scale, and this would be a normalized frequency, the frequency that you're at relative to the resonant frequency of the chaff. And so here's where it peaks and it drops off. So what you're going to want to do is combine in one package, if you've got some radars at C-band, S-band, X-band, you're going to want to combine in an individual package different lengths so they'll cover the band. And when you do that, this is what a multi-band chaff package would look like when you have 26,000 pieces that's 4.75 centimeters long, and just working all the way up so that it just in the millimeter wave region. You got 100,000 pieces, and at X-band 40,000 pieces, and you can pretty well fill up the area from 2 to 12 gigahertz with 40 meters squared of chaff with this. And this can be put in a reasonable package to drop out and cause havoc to radars. Okay. And the theoretical number of chaff dipoles required per square meter of RCS is given by this number, and it's 1 mil coated chaff. Now here's one of the ways that chaff is dispensed, and this is taken from a 1972 text by Fred Nathanson and re-rendered, and the chaff is put in rows of dipoles and made up like a big roll of toilet paper and coated in a roll. And these rolls are one after the other are in a dispenser, and a motor turns the roll such that it pulls the chaff out, and what you've got up front is an air cylinder that rams air in with an outlet at the front of the pod. The plane's front would be this way, and down the center is a pipe which takes the air, and as it unrolls, the chaff goes by the air duct that comes in, and when the air duct hits the chaff from the roll, it just breaks it up with huge turbulence. And like if you had two-sided tape, you've had it's got a take-up roller, and then the chaff is between two sides. It's on the take-up roll, so there's a take-off roller and a take-up roller, and then which pulls the chaff around. You have none left, and then this is pushed out, and the next piece goes down, and so there are 12 rollers each, and 6 air ducts all around, which cause the chaff to come out the end in a great turbulence burst. And this is one of many, many different ways that you can disperse chaff. And I'm going to show you a movie of a chaff drop and a test that was done down near Atlantic City, where we had a number of different radars instrumenting the chaff drop, and we used a British Canberra bomber, which the U.S. used a B-57. It was a medium bomber, and with an E next to it, it means it's used in electronic warfare. And it was used to test U.S. Radars in the 1970s. And we were down at Atlantic City, and of course you don't want to jam, which we did later on, but also drop chaff up and down the East Coast that would ruin air traffic control. So we did this test late at night. When we turned the radars on, there wasn't an airplane in the sky. And so what we did is we not only dropped the chaff, and you'll see the track of the chaff. It actually, this shows it as a route out and then a turn and then coming back. But the actual path of the EB-57 was a path out radially, and then after a while a dog leg to the right, and then it came back. And it may be that this is the shorter part of the path, and then this is the dog leg to the right. But in any case, it went out on this approximate triangular route, and we viewed it with a couple of different radars. One of them was an FPS-18 that was modified to look just like the Air Force's ASRs, and it had a good pulse Doppler processor, the first moving target detector processor that was built, hooked on as its signal processor. And I'm going to show you the results of when we had a Gulfstream aircraft fly through the chaff, its performance as we progress now. So here's the scenario of the start of the chaff's dispersal. What we've got here is we're looking at the normal video of a plane position indicator, a PPI. And we've got the threshold set just above noise level. So anything above noise level will show as a white dot, and that's just right there where we're beginning to drop the chaff. And these are range rings at 5-mile intervals. And this is way out at, you'll see later, in the many tens of miles, 30, 40 miles or something, out over the Atlantic Ocean. Now, when I show you the movie, we sped up, we took a movie of the PPI, and the actual data you're going to see in 30 seconds was 8.5 minutes of dropping the chaff and then letting the wind take the chaff. Okay? And you'll notice as it goes that this is at 15 nautical miles, so this is 25, 35, and this is 40 nautical miles away from the radar. Now, there's a 30-knot winds aloft, and that moves the chaff to the northeast. So you're going to see the chaff cloud disperse. Because there's a gradient in wind, it's going to get wider as the gradient and the winds are lower at different altitudes, so the wind will be different. But also as a net shift up of the chaff of 30 miles an hour, 30 knots, excuse me, because that's where the prevailing winds were from. And we're going to see how the gradient of the wind is going to spread the chaff cloud. Now, here is a movie, and I'm going to, first what I'll do is I'll just show you the movie once in 30 seconds, and then we'll go back, look at it again, and stop it, and I'll point out things about chaff. Now I hit the wrong key. I'll have to edit that out. Okay. Now you see the chaff being dropped, and then it took the dog leg. It's already gone out 15 miles, and then it stopped. It ran out of chaff. We ran the chaff dispenser at the fastest that the chaff would go out, so it would be the absolute densest. And notice that the chaff is spreading. As the chaff drops, it's being blown upward, but spread out. Okay, now let's look at it again. And notice it's very narrow, and then it takes a dog leg down, and that 400 pounds of chaff was just dropped in less than 20 miles. And you can't see it because the threshold was set sufficiently high. The chaff would have bloomed, but there were actually aircraft flying back and forth through the chaff, and I'm going to show you the output of that. Okay? Now let's go to the next view graph. Now, here we see at 15 miles, at 1.2 minutes, 2.7 minutes. Here we're out at 30 miles, 6.7 minutes. At the end, and then 14, 22. And here's the end of the chaff deployment, and the chaff is still there. And very heavy. How heavy? Well, we're going to see that in a minute. Here we remember I pointed out earlier that we had also, I don't know if you noticed it, but there was a radar called the WSR-57, which was a height-finding radar, a circular radar with a narrow beam that's used to detect weather. And this is that narrow beam looking at the chaff cloud at 1024 with no attenuation in the chaff cloud. And 4 minutes later, at the same angle, an azimuth of 90 degrees, we see, with 18 dB of attenuation, we still see a chunk of chaff, 27. And to get rid of all the chaff, you had to put in about 40 dB of attenuation. And that's, we took it with an S-band WSR-57. Now, here is where the proof is in the pudding of how well a Doppler processing can deal with chaff. Now, here what we're looking at is the same time sequence in these three graphs and these three photographs, and another 30 scans here and 30 scans here. And this was from scan 980 to 1009. And you see, these at first in the column are the raw radar detections before the tracker. And so these are the false alarms we got from the chaff, but they're all very, very random in time. And the Doppler velocities are that of rain, similar to rain. And here is the track of the Gulfstream aircraft going through the chaff. Now, if we look at the output of a 3-pulse MTI processor and a sliding window non-coherent indicating detector, we see good tracking, and these are just using the radar returns, not using any beacon returns. We see as the aircraft went into the chaff, we lost it. And here is the EB-57 after it finished dropping the chaff. But when we use the FPS-18 with the moving target indicator, and both of these two different radars, this was on an ASR-7, this was on the FPS-18, they were normalized to have exactly the same signal-to-noise ratio. We see that we track solidly the aircraft right through the chaff. And of course we see the aircraft dropping the chaff. It's interesting to note that when, I don't know if we'll see it later, but when we were actually dropping the chaff, the moving target detector detected the aircraft that was dropping the chaff, but it didn't detect at all the chaff that was dropped just previously. That was amazing to see. Now we look at the next 30 scans and we see these fossil, they're a little later, things have been a little more diffused, and we see the aircraft come around, go into the chaff, and come out. And here's the output we see from the MTI. We see some false alarms up here, and we see A little bit of detections in the false alarms, but in this whole leg we see nothing. And some of these you'll see in here, it's hard to see, are question marks, meaning the tracker detected it a little bit outside the chaff and then coasted, the track coasted as it went into. And here we see with the moving target detector, a nice clear track. And right up here we had 2 detections, which were probably a bunch of the chaff cloud that didn't disperse. But remember, that's 30 scans of data over a 30 by 30 mile region, and only 2 false track points, and really clear detection of the target. And in this case, we've got 2-mile range rings. So we're actually looking probably 15 miles by 15 miles.